Yes. Okay. So first of all, thanks to the organizers. It was a wonderful event. So what I'm going to discuss today is a research line that I'm following, one of them. And I thought it was, the idea is to give you a kind of overview of what I've done together with my collaborators on jamming and more recently in machine learning. Actually, I will not directly talk about machine learning, but I will try to see jamming in machine learning. So the idea is to try to show you that jamming is present in machine learning in some way, and try to tell you how and why. Okay, so let me start from simple things. Let me consider this problem. This is the packing problem. So you have n spheres of a given diameter and a box of volume V. And then you are asked to find an arrangement of the spheres in such a way that they do not overlap. Okay? So each sphere is a volume, this one, okay, in d dimension. And then you can define a packing fraction. This is just the fraction of the volume that is covered by the spheres, if you find a satisfiable arrangement. And this is a constraint satisfaction problem, because you have to arrange the spheres in such a way that they do not overlap. So these are constraints. But this is a different problem with respect to typical combinatorial constraint satisfaction problems, because it involves continuous variables. And this is what makes the problem very different from the usual combinatorial optimization problems. Okay, so you suppose that you want to solve this problem. What you can do is to try to do an algorithm. So the simplest one is the following. So what you can do is that you have these spheres that have a given diameter, then you throw them at random inside the box, and then some of them will overlap. And so what you can do is that you can try to relax these overlaps. So what you do is that you say, okay, I pay energy whenever two spheres overlap, and the energy is like this. So it's an harmonic. It's the sum of harmonic terms. So you define some gap variables. So these are the coordinates of the spheres. You take the distance and then you subtract the diameter. So if this is negative, then it means that the spheres overlap, and then you pay energy. So what you can try to do is that, given this initial configuration, you want to minimize the energy. So you just do gradient descent, and then you can, for example, if the density is not so high, you can reach a sad configuration like this. So of course, the result, the ending point of the gradient descent depends on the density or packing function. And so you can have these three situations. So if you are at low densities, then it's very easy to find a satisfiable arrangement of the spheres. And then you can expect that if you increase the density of particles, then you can end up in a situation like this, where you cannot remove overlaps between spheres. And then in between there is a point that is called the jamming point, where basically it's the point where you are not able to find, through this algorithm, a solution to the problem. So if you look to the energy of the system as defined in this way, this is 0 up to this point, and then it starts to grow. Okay. So of course you can say that this algorithm may be suboptimal, in the sense that if you arrange locally the spheres, you are able to find a denser configuration. And so what you can do is to try to explore a bit the phase space to try to find these denser configurations. So how to do that? Well, you follow an idea that was proposed in this paper. So what you do is the following. So since you want to, let's say jump energy barriers to go to denser configurations, what you can do is that you can add noise to the system. So instead of taking the spheres of the diameter that you have, you start from spheres which have a diameter that is smaller. And in this case, you can do it as small as you can in order to get a configuration of the spheres in which you don't have overlap. So this is very easy to find if the diameter is small. And then you consider these spheres as R-spheres, okay? So they cannot overlap. And then what you can do is that you initialize the velocities of these spheres at random, and then you run the dynamics of the system. So this will be a gas of R spheres. They collide between themselves and with the walls. You treat these collisions in an elastic way, and then you run the dynamics. And then while doing this, you start inflating the radii of the spheres. And so this protocol is called Lubachevsky-Stillinger protocol. So if you do that, and you are in 3 dimensions, typically what you get is this. So this is the inverse of the pressure, and this is the packing fraction. So here you have a kind of, let's say, liquid, so the particles can diffuse in the system. And then here there is a first order transition to a crystalline structure. And then if you compress the crystal, then you end up with a jammed configuration that is the densest one, because it's the crystalline one. So this is what happens typically in 3 dimensions if you compress slow enough the system. If you compress the system too fast, you can avoid this crystallization transition, and then you end up in a metastable branch that is called the supercooled liquid phase. That is exactly the same that what happens in gases. And here you get stuck, and I will show you what happens. So this is the typical scenario in 3D. So you can ask what happens if you increase the dimension. And what happens is that as soon as you go to higher dimension, finding the crystal becomes more and more difficult. And the main reason is that you are really trying to find a very specific configuration, and the phase space becomes very big as soon as you increase the dimension. And on top of that, you don't even know what are the crystalline structures in higher dimension, apart from very exceptional cases. Okay, so what you can do is that you can analyze what happens in very high dimension, and in infinite dimension we have a phase diagram that can be computed exactly. So this is the inverse of the pressure as a function of the packing fraction. All of these variables are scaled with the dimension in such a way that you get something that is of order 1. So these are not the original, this is not the original packing fraction, it's scaled in some way. But nevertheless, what you get is that you have a part of the curve that is really the supercooled liquid branch, where basically particles can diffuse. So if you look to the phase space, the system can explore ergodically the whole phase space. Then here there is a glass transition point. And beyond this point, if you look to let's say, the Gibbs measure, this is clustered in an exponential number of states. And what happens is that if you initialize the dynamics inside one of these states and you compress the system, so you inflate the spheres, you leave this equilibrium, let's say liquid branch, and then you just follow the evolution of these glasses upon compression. Okay, and what you can imagine is that each one of these curves, that is just the equation of state of each glass, it's the result of different compression protocols. So typically, if you compress the system very fast, you leave very soon the liquid, the equilibrium equation of state. Instead, if you compress the system more slowly, in finite dimension, you can go beyond this point, and then you can reach denser systems. So when you compress these classes, at some point you have a jamming transition. This is the point where these are spheres get in touch and you cannot compress the system anymore. And what we've seen is that, so in the last years we have studied a lot this phase diagram. What we have shown is that here, when you compress these classes, you have a transition that is called Gardner transition that really changes a lot the properties of all these glassy states at high pressures. And the jamming point lies inside this phase that we call marginal glass phase, because it is associated to soft modes in the system. Okay, so these two different protocols, of course, give you different packings. So in particular, you can expect that using this protocol, you can get denser packings. Nevertheless, the properties of the packings that you get at jamming are quite universal. So all the packings that you obtain in this way, or with less smarter protocol, are basically the same. So what are these properties? So the first thing that you can look at is the properties of the contact network in the system. So you have a packing like this, then you can look at the contact network, who is in contact with who, and then you can measure the average degree of the contact network. And it turns out that whatever you do to the system, you have an experimental, let's say, observation. These are, you can do it in a numerical simulation. And basically what you get is that the average degree of this contact network is equal to 2 times the dimension of the system. Okay? And this thing is called isostaticity. So if you have an average degree that is less than this value, you say that the system is hypostatic. If it is higher than 2 d, it is hyperstatic. Okay? So what is found if you consider spheres is that all these packings are isostatic. Okay? For example, if you change and you consider ellipses, then they become hypostatic. Okay. So that's the first thing. The second thing is the following. So, okay, here it's a bit cut, but so what you can do is that you can look at the forces between spheres. So how do you do that? For example, you have this packing, it's inside a box. So what you can do is that you can compress this box at the boundary, and there will be a contact force network that will spread all over the system because the system is rigid. Okay. So you have forces among spheres that touch, and you can, let's say, measure these forces in some way, and then you can make the histogram of them. And what you discover is that at very small forces, you have a power law behavior with a critical exponent here. And so this tells you that if you look to, let's say, local excitations in the system, which are like opening contacts, you have a kind of pseudo gap in the distribution of the forces that control these local excitations. So this is the first thing. So the second thing is that you can look at let's say, spheres that are not touching, okay? And you can look at the statistics of the gaps between them. So you measure them, you make the histogram, and what happens is that at very small gaps you have a power law divergence, and this is controlled by another critical exponent. So you have a set of critical exponents that appear in the microstructure of these objects. Okay, so there is, let's say, a third sign of critical behavior. This is the following. So suppose that you consider these glasses of our spheres that you are trying to compress. So these are glasses, which means that if you are at high enough pressures, particles cannot diffuse in the system. So they just vibrate inside the cages that is formed by the surrounding mass. And what you can do is that you can measure the typical size of the cage in which each particle vibrates. Okay. So you call this delta EA. And then you look at the evolution of this typical cage size with the pressure, so as you compress the system. And so it turns out that it should go to 0, just because when you reach jamming, basically particles are blocked. So this cage size should go to 0, and it goes to 0 with another power law behavior. And this is another critical exponent. Okay, so what we did is that we made a theory for these objects in very high dimension. And that's what you get. So you can compute exactly these power laws, and they take, let's say, non-trivial values. This is infinite dimension. And this is how they compare with numerical simulations actually in several dimensions. So these points are for simulations from 3 to 8 dimensions. So the first thing is that it seems that the thing that you get from infinite D agrees quite well with the numerical data. The second thing is that you cannot at least we don't see any systematic deviation from infill theory. So if you, I mean, all these data seem not to depend on dimension, apart from some caveats that I will not tell you about. So these exponents seem to be kind of universal, and we still don't know why. Okay, so you get the values of the exponents, but you also get isostaticity. So you can show that packings in very high dimension are isostatic. Okay, so now let me make a jump. So it's completely unrelated problem, and this is supervised learning. So suppose, what is supervised learning? So you have, so this is a branch in machine learning that wants to classify things like images. So for example, you want to distinguish images in cats and dogs. Okay, so you'd like to have an object that you feed with the image, and then tells you if it is a cat or a dog. So this object is a function. Okay, it is very complicated. It has some structure. Okay, but this is not very important for the moment. And this function depends on some parameters that you want to fine-tune in order to be able to classify the images. Okay. So you have a set of, let's call them neural weights, W, and then you want to find these neural weights in such a way that if I put here the picture of a dog, then I get a dog outside. Okay. So the result of the computation of this function on the input of this image gives me the output a dog. Okay. So typically what is used in this field is systems in which these neural weights are continuous variables. And there are two main reasons for this. So the first one is that you want to train these objects. Here training is just the process through which you find these weights. And how do you do that? Well, you just have a training sample. There is a set of images that you know the labels. So you have a set of cats and dogs, and you know that they are cats and dogs. So you feed these images to this network, and then you require the output. And then you try to find by energy minimization, and here the energy can be, let's say, just the number of errors that you make. So what you want to do is that you want to try to minimize this energy. And so if you have continuous weights, then you can use like differential algorithms, so just gradient descent, for example. So this is the first reason. The second reason is that when you have continuous weights, these machines are more robust. Just because if you change a bit the input, this doesn't trigger any avalanche that you may, for example, expect if you have discrete weights. So if you change a bit the input, then these weights may change a bit, but the result can be the same. So there is an idea of robustness in having continuous weights. So once you look at the training process, that is the process through which you want to have all the training set to be, let's say, fitted by this function. So this is a constraint satisfaction problem, because you want that each input-output relation is satisfied. So these are a set of constraints. And again, since the weights are continuous, this is a constraint satisfaction problem with continuous variables. So you can expect that there is an analogy with Pagnos spheres. Okay, so what is the simplest model that you can use to study this? So this is the perceptron. Actually, it's a machine that does linear classification. So you have two sets of points, and you want to find a kind of plane that separates the two. Okay, and what you do is that you just take, so each point has a it's identified by a vector. So you have neural weights, and then you want that the sign of this scalar product gives you the label. So if you are below this plane, you have tau equal to 1. If you are above, you have tau equal to -1. Okay, so you have this relation. These are the constraints. So you can translate this into this thing. And you see clearly these are a set of constraints for these variables. So what people do is that instead of requiring that this object is greater than 0, you want to have a kind of stability that tells you that these points must be a bit far from the boundary in order to have robustness with respect to noise admission. So what you say is that you have this thing that is greater than some parameter sigma. Okay. Now what you can do is that you can say, okay, let's suppose that I want to learn random data. Okay, I want to try to find an hyperplane that separates random vectors. Okay. So this problem was solved by Gardner and Derrida in 1988, actually at the IPhT, because Derrida was there and Gardner was visiting. And you get a phase diagram like this. So here you have the number of constraints, and here you have this parameter sigma. Of course, the problem as a machine learning problem makes sense only if sigma is positive, and this is what has been studied by Gardner and Derrida. You can look at what happens when sigma becomes negative, and you get a more complicated phase diagram that shares a lot of similarities with our spheres, but I will tell you more later. And this is something that we did recently in these papers, and if you want to know more, there are these lectures that I gave in the lab. Okay, so I don't want to go to problems that are not machine learning problems, and here, I mean, it's a machine learning inspired model, but I want to really consider models that you can try to use in machine learning. And so what we did recently is to go beyond the perceptron parameters. Okay, so the perceptron does linear classification. So you have just an hyperplane that separates the two sets. Of course, if you have more complicated data, you can expect that these are not separated by a plane. So you need to have a more complicated function. And the simplest thing that you can do is that you can add, let's say, a hidden layer. Okay, so you have here the input, then you have here an hidden layer, and here there is the output of the machine. So what you do is that you have the weights of the machine that are here, and then what you do is that you compute this hidden, let's say, local fields. There are just this scalar product between the weights and the variables that are input here. And then you have a set of variables hi. And then you can choose different output functions. What we did is to consider three output functions, but let's focus on this one. So what you do is that you say that the output is the sign of the product of these variables here. So this is called parity machine. So the output is just the sign of the product of this object. Okay. Now you can redo exactly the same thing as in the perceptron. You say, okay, I want to classify random data. So the problem is no more a classification problem, it's just a satisfiability problem, because I just want to fit random data. And then you can define gap variables. These are analogous to what you have in spheres, in which you have in which you look at the distance between spheres. Here you can do the same, and here the gap variables are this. So these objects are positive if your weights satisfy the constraint that the input-output association is done correctly, and it is negative if it is done incorrectly. So here the constraint satisfaction problem is that you want to find these W's in such a way that all these gap variables are positive. Okay. So you can study this problem through the main through the same techniques that you can apply to R spheres. Actually, the equations that you get are more complicated because they are kind of higher dimensional. But the result that you get is is basically the same. So this is the number of constraints that are unsatisfied when you go in the unsat phase. So suppose that you want to learn a lot of patterns. At some point you go in a phase where you are not able to find a set of weights that satisfy all the constraints. You are in the so-called unsat phase. And then you can look at what happens when you decrease the number of patterns that you have to learn. And what you can measure is the number of unsatisfied constraints that you have. And this number has a limiting value that is 1. Okay? And actually this one, it means that it's the system at the point where you start to become unsat, that is the jamming point, is isostatic. Okay? It's like our spheres. You can also look at the statistics of gaps and forces. So for example, here gaps is just the statistics of these variables when they are strictly positive. Okay. And then you get a power law behavior at small gaps. And the power law, this is the cumulative distribution. Okay. So if you look to this thing, then if you look to the density, then you get a power law divergence. The cumulative has this behavior. And this law is exactly the same that you have in our spheres. So the critical exponents that you get here are exactly the same. And we can make an analysis, a theoretical analysis of these models, where we can show that that's the case. You can also look at the statistics of contact forces. So how do you define them? So you go a little bit in the unsat phase. So let's say that you are here. You have a set of unsat constraints. And then you measure the modulus of the gap. So these gap variables are negative. You call the modulus the forces. And then you look at the cumulative distribution. And again, you have a power law behavior. And this is well fitted by exactly the same critical exponent that you have in our spheres. Okay. So, okay. Yes, thank you. So let me just tell you a few words about what we expect from all this. So these are constraint satisfaction problems. As I told you, they were studied a lot when you have discrete variables. For example, if you consider K-SAT is a famous, very famous constraint satisfaction problem. So what I would like to tell you is that these problems are richer because their phase diagram is richer. So the typical situation is the following. So you have a bunch of phase transitions. So when you start from, let's say, a situation in which you have few constraints, then the space of solutions of this constraint satisfaction problem is a kind of very big wide region where you can go from one solution to another. Then there is a dynamical transition that has exactly the same nature of the glass transition in our spheres, where basically this phase space cluster. So you have a lot of clusters of solutions, and if you are inside one of them, it's very hard dynamically to find another one in another cluster. So you have an exponential number of them, so you have a complexity associated to them. And when you increase the number of constraints, this complexity decreases. So you have at some point a condensation transition, where you have a sub-exponential number of these clusters. And up to this point, everything is exactly the same as in combinatorial optimization, standard combinatorial optimization with discrete variables. The point that happens here, the main thing is that when you increase the number of constraints, these clusters acquire a kind of structure. So they become clustered themselves in a continuous way. And this is what is called the Gardner transition, and it is exactly the same that you get in our spheres. And this transition is what gives you all this critical behavior and all these critical exponents. And then when you increase the constraints, at some point you have a sat-on-sat transition. Okay, so that's the generic scenario. So the conclusion, what I showed you, is that these problems that have been studied a lot in statistical physics and condensed matter actually are deeply related to constraint satisfaction problems, and also to supervised learning. And what I've shown is that if you go to multi-layer supervised learning, you can get these situations. So there are some perspectives. So what has happened in the case of combinatorial optimization is that if you know the landscape of solutions of this problem, you can design algorithm to try to find efficiently solutions. So here we have exactly the same problem. So we would like to find solutions efficiently, but the problem is that the landscape is more complicated. So how to design algorithms that are able to find, for example, solutions up to the satisfiability threshold, this is an open question. The second open question is that what I've shown is that you have two very different models, machine learning and hard spheres, that basically share exactly the same critical behavior. So it seems that there is a kind of big universality class, and the main question is why, and we don't know. And the third thing that is something that I didn't talk about is what are the generalization properties of these objects? How do they depend on the landscape? So, of course, understanding these problems will give us also algorithms to get, for example, machines with better generalization properties. So here generalization is the property that, I mean, if you are really looking at a machine learning problem, once you have trained your network, you want to measure how much it is accurate. So you take another example to classify, and then what you would like to know, how much the machine that you have trained is able to classify correctly the new example. So hopefully this understanding the space of solutions of these objects will also give us a way to get, for example, machines that generalize better. So for the moment, what people do is to use like gradient descent algorithms or stochastic version of them to train the networks. And the hope is that if you use these techniques, maybe you can get networks that generalize better. And this is something that it's something that I will work in the next months. Okay, thank you.
Thank you very much.
Let me ask about more elementary, maybe more aspects of your this packets which you get. For instance, you mentioned that that you often get this. I forgot the name of this property, but contact number is equal to 2D.
Yes.
And of course, we know actually perfectly, latest configuration is exactly contact number equal to D. It would be hypercubic, And that hypercubic, lattice would be, of course, very, very sparse. Its volume fraction decays like 1 over d factorials. Mm-hmm. And so I just wonder, what you get using your dynamical procedure, how much better it is, volume fraction, but in that real units where you kind of, you consider really a fraction of volume covered by spheres, and also how far it's away, or what's the relationship is. But essentially the only known, very minor improvement of lower bound, and lower bound, Minkowski bound to the minus d.
Okay. Okay, so this is something that is, okay, I can tell you. Okay, so actually what happens when you look to this, so it happens that if you go, let's say, to log d far away here in this direction, so So the first thing is that this variable is 2 to the v divided by d times the packing fraction, the real one. Okay? And so when you go to order log b in these units, then you have a condensation transition. And then if you compress, let's say the high pressure phase that you get there, then you get a jamming point that's far away. This is the point where you get the maximal dense amorphous packing. And this packing is in between the two bounds that you can get in ID for the densest packings. So you don't know if there are denser packings that are not amorphous, that are like lattice packings, because this thing is really in between the two bounds that are actually far away.
Any further questions? Don't seem to be any. So thanks again, Pierfrancesco, and we will be moving